Hello, 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 and welcome back to another episode of Kerbal Space Programming. Kevin here, and I am very excited for today. We let a computer figure out how to send this rocket into orbit. We talked about genetic algorithms a bit in the last episode. We talked about our own approaches to a good ascent profile, but this time we are letting a computer try and solve it. And there we go. Our genetic algorithm is initialized. Let's take a look at what exactly we're doing today. So what we just ran was the genetic algorithm initializer. And now we talked about genetic algorithms in the last episode, but as a refresher, what you're doing when you're dealing with the genetic algorithm is you're taking a population of possible solutions to a problem and you are giving them a fitness score. So you're ranking them as to how well they did. You're going to select parents from that population and say, all right, we're going to take you and we're going to combine you to create children. You're going to introduce some mutation to those children, and then you're going to say that's the new population. And you do this over and over and see if you get a better population out of it. Now, I've abstracted this out into two libraries, genetics and float. And the reason for this is, just to kind of make our job a little bit easier. The genetic library is going to require us to write a function called GA fitness, which takes in a chromosome and gives back a score because it doesn't know anything about what problem we're trying to solve. And it requires us to represent chromosomes as series of ones and zeros. So there are a couple of reasons why this is beneficial. The way that we can combine these, when we have two parents, let's say these are the two that we selected, we can determine some arbitrary cutoff point and say the two children that you two provide look like this. We'll take the first half from the first parent, and we'll take the second half from the second parent, and then we'll take the first half from the second parent and the second half from the first parent. Or we could determine some other arbitrary cutoff point. And in fact, it's random the way that we've set this up as to, there we go, as to where it decides to pick this stuff up. So the other reason that this is great, let's just say that this is one of the children, is that when we're looking at how do we mutate these, well, we can say we've got that, and we can just flip a bit from 0 to 1, 1 to 0, and that whole thing. But of course, when we're actually doing stuff, we want to be dealing with numbers, and this is why I have this library called float. This is going to convert a number into a string of zeros and ones and back out. Of course, those are not the right values, but you get the idea. So what we've done here is we've said we've got a size. We're going to have a population of 20. We're going to set a list of chromosomes, and we're going to go ahead and take in a whole bunch of values. So what we're going to do is we're going to say we've got a bunch of stuff here. So the first one is we're going to tweak our thrust to weight ratio based on the percentage of altitude that we've achieved. We're going to adjust our pitch based on the percentage altitude that we've achieved, and we're going to set a cutoff for our apoapsis. So what this is going to do is we're going to say, let's say that we have an altitude percent, so that whatever target we're trying to get to, we're halfway there or whatever. We're going to say your pitch is going to be, A times alt percent to the B plus C. We're just going to use a regular standard polynomial equation or math formula for those who are scared of polynomial equations. And if we imagine what we did kind of before when we were doing our own manual attempts, is we said something like we want our pitch to be negative 90 times alt percent to the to the 0.5 plus 90, so that when this alt percent is 0, the pitch is 90, and as this alt percent rises, we start to subtract 90 from the total. So we're letting the genetic algorithm basically adjust these three values. We're going to do the same thing for the thrust, and then we're going to have a cutoff, which is basically saying this is the point where once your apoapsis is at this altitude, you can go ahead and throttle down. So we're actually letting the genetic algorithm tweak these 7 different values, and we're converting them to these bit strings of ones and zeros, and we're adding them all together so we get this very long chromosome that describes our solution. Then we're going to call GA init, which I've written into our library. It's going to go ahead and take those chromosomes, write out information to a file so that it'll save things there and know what the state of the population is when we revert, and then we just notify that we've initialized. So let's take a look at how we actually launch stuff now. All right, so here we are actually iterating. We're going to switch to the archive volume, run stuff, load up the terminal, and display some stuff. First thing we need to do is actually figure out how to score a launch. When we're done with a launch, how do we determine how good of a launch it was? Well, first off, we're going to get the fuel resource so that we can measure that, because that's going to matter. I'm going to skip over the penalty score for the moment. We're going to look real quick at 3 scores. We've got an apoapsis score, we've got an eccentricity score, and we've got a fuel score. Now, what I've assigned these to is Gaussian, and this is a function that I've written, and we're going to jump over real quick to Wikipedia to explain what that is. So this is a Gaussian function, and basically you can see it's just a bell curve. We want a value between 0 and 1 that's not going to necessarily be linear. And you see this is this complicated formula, but it has these three values that we can tune. One of them adjusts the height of the curve, one of them adjusts where that peak is on the x-axis, and the other one adjusts how wide it is. So I've gone ahead and just picked some values that seem to work. We're going to assume that we're always dealing with a maximum value of 1 because our score should be a value between 0 and 1 because that makes things very easy. And then I've adjusted the width because some of these values we don't expect to get to orbit with 100% fuel, so we needed a different curve there. So this Gaussian function takes our apoapsis, it takes the target value, which is the peak on that curve, and then we've adjusted a width here to say where is the halfway point of that curve. And the eccentricity is different because the eccentricity is already a value between 0 and 1. So we go ahead and do the same thing. We're going to grab the fuel amount divided by the fuel capacity, so just the percentage of fuel that we have left. And then we're going to compute a total score. We're going to say we're going to take the total plus the apoapsis score times 10, because I care much more that we got to the right apoapsis than I do care that we had a lot of fuel when we got there. Then we're going to set the eccentricity score times 5, and then we're going to add the fuel score. So a perfect launch could get a score of 16. Now what we're going to do is we're actually going to look at this penalty score. And here I've actually set up this altitude score that's a minimum of the ship apoapsis divided by 100,000 meters. And this is basically just a way that we can scale things down, because we're going to subtract that from 1 and divide it. To make sure that if you didn't actually get up into space, well, your score is going to be heavily, heavily penalized. If you got to space, then great, your score is going to be times 1,000. If you didn't, it's not going to be times 1,000, and so you're not going to compete. This is just to make sure that we don't end up in a situation where it says, all right, well, if I save 10 fuel, then I can be 1 off of my apoapsis score, right? Just to make sure that we don't have these things fighting with each other, that we want to say, all right, do that, but make sure that you actually get to space, please. That's really what we care about, first and foremost. And that's how we're going to go about scoring our launch. And then we're just going to return that total. And then we've got this Gaussian function that's just the stuff that I described. Now we actually have to run the launch. So we've got our chromosome, which is that string of zeros and ones. We're going to unpack out those zeros and ones. You see, in a couple of places I've actually inverted it. So we may have a value that is 5, but we're actually looking at 1 over 5 as these multipliers or things like that. So I'm grabbing all of those out and grabbing the cutoff. We're basically just using this toFloat function that comes from the float library I wrote that turns these zeros and ones into a real number. We're going to print out that information to the console. Then we're going to go ahead and launch. We'll lock the throttle to 1, lock the steering to up, wait 5 seconds because we're not letting this thing control until we actually get out there. We're going to lock our percentage altitude to how close are we to 100 kilometers. And then we're going to handle the throttle control. Now, we've done this in the past. We're basically getting our available thrust to weight ratio. We're calculating our max thrust to weight ratio using that formula of a multiplier times our percentage altitude and exponent plus the offset. And then we're going to lock the throttle to that, but making sure that it is bound between 0 and 1. That's what this min-max is doing. We're going to do the same thing for pitch, multiplier altitude to the exponent plus the offset, and lock the steering to 90 east, but then whatever the pitch should be. Now I've also got it set to turn on the lights. There aren't lights, but we've got an antenna on there once we get out of the atmosphere. And now we have a bit of a mess. These are all of the ways that I figured out that things could break. We need to figure out a way to end our launch, or to say that we're at least done trying to figure out what our score is. I'm going to save our part count so we know how many things there are on the ship, so that if anything falls off, we can know about it. First thing I'm going to do is I'm going to say if our apoapsis is above the cutoff point, then we'll throttle to 0. We'll say if we are above the cutoff point and out of the atmosphere, great, we're done with our test, nothing's going to change. If we say we're in the atmosphere and our vertical speed is dropping, you're done. We know what's going to happen there. If we're out of fuel, you're done. If we are above the atmosphere and close to our apoapsis, you're done. If the apoapsis and periapsis are both are above 100 kilometers, you're done. If we don't have a connection, you're done. If we have lost a part, then you are certainly done. And if we are out of electric charge, you are done. Now, I didn't have all of these in place when we started testing. I've added kind of incrementally these various ways that, okay, no, your flight is over. You get a score now, and then you're done. So what this is going to do is then when we're done, we're locked to the throttle. We're going to get that score. We're going to notify that score out. And we're going to really try to get a connection. We're going to turn on the lights even if we're in the atmosphere. So deploy the antenna and then really hope that we can log stuff out. We're going to log set last fitness to the score to a file called lastfitness.ks, and then we're going to revert to launch. So this is our launch process when we need to actually get a score for a chromosome. Now we actually integrate with the genetic algorithm library. We've got a function called GA-fitness, which the genetic algorithm library expects to be defined. It takes in a chromosome, and then we're going to say, all right, if there's a file called lastfitness, then I'm going to presume I already ran that. So I'm going to go ahead and run lastfitness and then delete it, and then I'm just going to return the value from that. So the reason for this is when we revert, the programs are going to start over. So we need a way to make sure that we can say, all right, here's what the fitness score was. I'm going to revert to launch. And then when it boots up again, I'll go, oh yeah, I just ran. This is the score for that. Otherwise, then we'll go ahead and say, yep, I haven't run anything already. So go ahead and run the launch using that chromosome. And then we've got this function here called GA-next. And what GA-next is going to do is it's going to look at the population. It's going to say, do any of these need a fitness score? If so, I'm going to call GA-fitness on them. Otherwise, I'm just going to grab a new population. And so this will mean we can run this ideally forever and generate new populations. Let's see how it works in practice. And on the launch pad, first flight, all right, did not do too well. And the second one did not do too well either. But the third one seems to be doing roughly okay. It's tilting over pretty aggressive. Okay, nope, it's going vertically again. This is what happens when we generate kind of random numbers, that those first two basically just didn't have enough thrust to keep the thing airborne, which means that we ended up with problems and that it immediately detected that we were in the atmosphere and our vertical speed was dropping. So it said, all right, your test is done. We're going to go ahead and give you a score, write that out to file, and that is what it is. And then the next time after we revert it, it's going to go, hey, here's the score for the last thing you asked for. Go ahead and use that. And then it'll go ahead and run the next one. You see, I've got a couple of artifacts because, as a matter of fact, this ended up taking I tried to calculate it out. It was about 5 days of real-world time to run all of these generations. We've got a population of 20, and right now, in our first generation, a bunch of them are failing pretty quickly. But once we move on further and further and it starts selecting the better and better parents, we'll find launches that take 5 to 7 minutes. And when you're running 20 of those for every generation, and you ideally want a bunch of nope. Nice, you shall not go to space today. Yes, but when you run a bunch of those and you want to have a bunch of generations, this ends up taking a considerably long amount of time. So there is some artifacting because this is terabytes and terabytes of video footage. And, you run this stuff for a while and eventually some of it gets corrupted. So you see there we've got that interesting behavior where it launches and then it tips over wildly and then manages to right itself. We're going to see that happening quite a lot throughout this successive approximation mechanism. Nope. I don't know exactly what the... Oh, okay, you decided you're going to go that way. Good luck with that. Yes, and as you see, so our first generation is not so many winners. We had a few of them that lasted a few minutes, but most of them did not. Of course, this is playing back, I think, at 8 times speed. When we jump in and take a look at further generations, we'll speed this up to, I think, 160 times, because, man, this gets really old. Overall, running this, we ran a total of 50 generations of these, and that totals to 1,000 different launches. And here we are jumping ahead to generation 7. So you see that over time this has actually managed to correct out a bunch of those throttle problems because it is merging from the best generation by generation. There's still a couple, and of course now we're in 160 times time acceleration, so the bad ones do not last particularly long. But yeah, you'll see that dip there still exists and is still a bit of an issue. And I think one of the things that we probably could have done, but of course this did take about 5 days to actually run, so I'm not inclined to go ahead and start over on it, is we probably could have also had this thing tune and play with a minimum speed or minimum altitude at which to start its turn so that the formula that it was trying to tune could account for that. Okay, that one is crazy. You see, now it is sort of, this is okay, so this is another thing, is that when you revert over and over and over, eventually, KSP doesn't like that. and it will crash. So I could leave this thing running for maybe an hour or two, but had to be around to kind of restart these things. Thankfully, because we have everything logging out to the archive volume and then picking up where it left off, once we return back to the Launchpad, things start to get a heck of a lot better. And so you can see that these are slowly evolving into a particular kind of pattern. Some of them are taking, a mostly upward trajectory. The other ones are doing that little wobble where they move over to the side. And it seems that the ones that do this initial upward launch end up, you see a lot of that heating effect as they start to get up there. Well, that one didn't. There we go. Maybe. We're starting to get there. And of course, we're not actually seeing the apoapsis or periapsis, because this isn't even trying to circularize. It is just trying to get an efficient launch. Okay, now we've jumped ahead to generation 20. You can see most of these, we've got those crashes again. Most of them have settled on this much more vertical and gradual takeoff rather than the instantaneous side and then flip back up. But we do see a lot of those re-entry heating. And of course, that one managed to crash. I think that was before I added one of the final edge cases of maybe it's if you're running out of battery. I don't entirely remember what was going on with that. Well, okay, another one. Of course, because we are allowing for random mutation, because of the way that these numbers are encoded, it is possible by flipping a single bit in that string of ones and zeros to turn a number into a negative number, or to turn a fraction into an exponent. Or a fraction into a scalar value, because the way that floats are encoded is that you're using, you have a sign bit, and then you have an exponent, which can be positive or negative. Yep, lots of these. And then you have the actual significant portion that gets multiplied by the exponent. So it is actually easy for these things to kind of flip and go crazy. But up here we're at generation 24, and you see that we're not seeing a huge amount of those failures. Obviously it's still possible for us to immediately go, hey, we think we should have a negative thrust, and those will die off really quickly. But the majority of these things in the generation tend to be lasting a reasonable amount of time. Now, of course, I was not able to record the entire iteration of this because, frankly, I ran out of disk space. So we're ending up kind of looking at this selection as time goes on. But we're about halfway through our iteration, though I think I recorded fewer of the successful generations because we started to get kind of diminishing returns, which is expected. Now we're on generation 36, and you're seeing that we're seeing mostly similar sort of stuff, though we are looking at still kind of that overheating issue, which may mean that these are not the best solutions. And now here we are finally at generation 50, which is the final generation that we ran because, I had to get this video up at some point. Theoretically, we could go ahead and just continue where we left off, and we've still got a couple that flip out and go crazy, but the majority of these are at least getting pretty reasonably close to where they ought to be. Despite the fact of that overheating. So as soon as this wraps up, we can now jump back and take a look at how things progressed over time. So I've gone ahead and mapped out the generation scores over time, and unfortunately in this series of 50, the first two I actually had scoring a little bit differently, so we've kind of got to discount those. But by generation 3, we were using the appropriate scores. So we can see here's kind of the range of scores out of all of the generation. The top score that we got was 1600, and the lowest score was 3, because remember, we are massively scaling things down if it didn't actually get to the altitude before it died. So we've got one that seems to have gotten to altitude but did not get very high scores. It got what would have been kind of 1.6 normally, but times 1,000 because it got to altitude. And we can see that really quickly this starts to pick up. We get at generation 5, we see one did really, really well. It got a score of 15,376 point something. And we've got the median here that is just kind of the middle point between all of these generations. We see that there's a lot of fluctuation, and in all but one of the generations, something pretty much failed on the launch pad or just off of the launch pad, because we have these scores of around 3 here, which means that didn't get to altitude, died early, but somehow in generation 10 it managed to avoid that. It didn't get a high score, but it did at least get to altitude, so that was a good generation. Now we can see the median kind of oscillates, but it seems to be getting better, that overall the majority of these tend to be doing okay. And our peak score is actually here in the 28th generation. It's not at the end, so I don't know why we ran the rest of these. The peak score was 15,797, and out of a maximum, if we think about we had something times 10, something times 5, and then something, well, that means that we could have had 16, because the scores are all between 0 and 1, then we multiply them by 1,000 if they got to apoapsis. Well, then 1,600, or 1,600, 16K, what? 16K, what? 16, yes, I'm sorry, 16,000. Yes, is the maximum score. So this is actually incredibly good. That's remarkable. And then our median dipped back down considerably. That did not seem to take off. So over time, we got that maximum score, but when it combined with parents, it didn't. I guess it must not have lasted. And we can take a look, and eventually, once we get out past 40 generations, we see not much in the way of improvement. And in fact, these past 2 generations did not get anywhere near the high score. The maximum range is not so great. So just to kind of look at how this thing went about solving its problems, let's take a look at that 28 score, because I do have these logging out all of their chromosomes every generation. Let's go ahead and run that, and we'll go ahead and look at the telemetry and see what exactly happened on that flight. So because all of these chromosomes are saved in a file, I was able to just go ahead and load it up and say, let's go ahead and run it, and actually run the telemetry that we've done on our manual attempts, or well, not manually, but custom. You see, yeah, it did that dip there, which is very weird, and we certainly didn't see that toward the end of our generation. So makes me a little bit skeptical that maybe that strategy is not the best, and we certainly did see a bunch of failed attempts where it started tilt over and then ended up losing vertical speed while in the atmosphere. So a little skeptical, but you see it is throttling down to maybe 30% and getting itself up there. But unfortunately, at around this point, we actually lose connection because we're going very, very fast while still in the atmosphere, and so our telemetry ends there. So let's jump over and take a look at what we saw. So looking at the ascent data from there, we can see that our apoapsis was never really more than 2 kilometers higher than our current altitude. We kept it pretty much in parity, which means that we were probably spending most of our effort on lateral velocity until finally things really, really shoot up here at 96. Now, we did lose connection with the probe at the point where altitude was about 40 kilometers. So that's all of the data that we have, but presumably it would have been close to cutting off at that point anyway. So, this is a reasonable amount of data. What you can kind of guess here is that basically we're devoting just as much effort as we possibly could to pushing out our periapsis and trying to kind of circularize and then almost do kind of a transfer orbit from an in-atmosphere orbit to something that's going to get us out of the atmosphere. And we did get to, just about 100 there. If we go ahead and remove the apoapsis and remove the altitude. Next thing we get to look at is our delta V. This is, declining at a fairly linear rate. And at the bottom here, when we did have our apoapsis that was, very close to our target, we ended up with about 450 meters per second left, which I think would have been probably enough for us to circularize and finish up our orbit. If we remove that, and now we can see wherein this problem lies. What was going wrong with that launch? We've got here our angle that, our real angle, and here is what our target pitch was. We can see that right at the beginning, it wants to pitch over to 80, and then it wants to pitch down to 75 degrees, and we're not going very fast, we're not very high up. That's not a great idea, and what it looks like happens is that basically we lose control, and then just barely manage to regain control to get back up to our target. And at that point, then we seem to match up. And I think this kind of explains why we saw that the majority of future craft never kind of got to this point, because when you have an ascent profile that relies on you toppling out of control and being able to recover, my guess would be that this was more of a fluke, and that the majority of the crafts that tried to adopt this very rapid target pitch strategy ended up kind of spiraling out of control. And that's why we saw toward the end of the generation stuff that took a much more gradual ascent profile and was going much more vertical toward the beginning of the flight. So this is probably why that's the case. And we might want to look at, kind of the later generations that, even though they didn't score as well, probably did pretty reasonably, just not as well as this random one that managed to find a way to recover from some sort of spin out. And here's where things really start to look fancy. The eccentricity, which remember, 1 is not a circle and 0 is a circle, and we're not tricked by scales here. This does go down to 0. We can see that by the time we were down here, we were incredibly circular. 0.06 of, close to circular, and that is at an altitude of, about 40. So we really were going in kind of a circular orbit at 40 kilometers, and at that point we started to push our apoapsis up, so we're doing kind of more of a transfer orbit than trying to get into the atmosphere. And then here we see our target throttle, and we can see, okay, the target throttle did seem to be important, that because we set that cap on, we had played with the idea of, just go full throttle and try and tune your angle to match. Well, it seems here that it did converge on the idea that no, limiting your thrust is a reasonable idea. So that's at least useful to know. But of course, the proof is in the pudding, as they say. And we can see here, this has an apoapsis of a little over 80 and a periapsis that is not 0. It would take us very, very little fuel to actually get this to where we want, and certainly is far better than I would be able to fly manually, and leaving over 450 meters per second of delta V. I would say that computers are a massive success, and I'll see you next time. Cheers.